All right, so welcome, guys. We're officially starting review. I wanted to focus on rotation because I know rotation tends to be a really hard topic for us. We're, of course, going to go over everything at some point. That's fine, Eduardo. Like, I'm not grading you guys hard. And so, yeah, so if any of you are like worried about how well you've done the test, the fact that you took it, I'm going to just give you points for it. Regardless of how well you did. I really do want us to look over that because especially with the test being only 45 minutes, I'm like really hoping, because sometimes I think our issue is just concentration duration. We just can't concentrate that hard for that long. So I'm hoping the 45 minutes will sort of give you guys like, yeah, it's fast, it's hard, but you only have to focus for 45 minutes. So a class period. Yeah, so as far as like timing it, I think I'm going to do more timed FRQs for you just so you guys have the practice at them. And you guys get really used to like how to upload different things. Of course, you can turn them in offline. I'm not really going to care about that, but I do want to give you guys different chances to do those. I didn't know my test started. Oh, yeah. I guess the good thing about the actual AP test there, Alana, is that it's going to be very distinctly timed. Like you started this time, you ended this time. They recommend that you get online 30 minutes early, but we'll talk more about that as more details come up. So again, first thing is try this. So this is a rotation problem because we're rotating a pulley. This is not a massless pulley. It has some rotational inertia or moment of inertia. So what do you think is going to be different between if we attach a 20 Newton object to it versus if we just pull down with a constant force of 20 Newtons? Will this be the same or different? So go ahead. Feel the same, or are there going to be any differences between these two? Should I call on people? Cool.
Wait, what's going on?
This daily quiz.
Okay.
So, Cindy, you want to take a crack at it?
I guess so. So I think it'll be the same.
Okay.
But I'm not sure yet because I was trying to work it out with the torque equation.
Mm-hmm.
Like RF sine theta is the same for both, but I don't know if inertia times acceleration would be the same.
Okay. All right. Iceland?
I also thought it would be the same, but I didn't have a specific reason as to why.
Okay. Alex?
I think it's the same because force-wise, I mean, it's the same force being applied to the thing. So, like, it has the same force and it has the same mass. So it should have the same acceleration.
Oh, you brought up a really good point. Excellent point.
Oh, wait, it's not the mass.
They don't have the same mass, do they?
Mm-mm. Only the same force.
So they do have the same force, which is excellent to point out. But this has some mass, and this has some mass. In this one, our rope really probably doesn't have any like mass, or very, definitely less than 20 newtons. So that's something we should consider, that they're probably not the same mass. All right. Anything to add on that, Danny?
Give me a minute.
Okay. All right, and so we do want to consider our torque equations here, but we also want to, the book actually like has a different way of solving it, but this is the way I thought about it, is I also wanted to think about like what is going on with my net force here versus my net force here.
So you would solve it as a force problem? Like the ones that we used to do from off of the desk
I would.
onto
Yeah,
nothing?
it's like a force to a torque problem.
Oh.
So basically, if we were to draw a free body diagram of this situation, we have our force, or our object that's causing the force. It has 20 newtons of gravity. How much force is it applying upwards, or is being applied upwards on it? Equal to 20, more than 20, or less than 20?
Less than 20?
Yeah, because which way is it accelerating?
Down?
Yeah, it's accelerating down, which means our net force needs to be down, which means whatever force this is, it has to be less than 20 newtons. And so for our object, it's getting pulled by that same string, but that tension is less than 20 newtons. So how would the acceleration be different in these two objects, or these two scenarios?
Would one of them speed up and the other one would be like more constant?
They both would accelerate or have an angular acceleration, but will they have the same angular acceleration?
No.
No. Which one's going to probably accelerate faster or have a higher magnitude of angular acceleration?
The mass?
The one with the mass or the one without the mass?
With?
You were calling me?
All right. It's going to be the one without, actually.
But like, doesn't the other one have less tension and then but more force being applied?
So no, the tension is the force, right?
Oh yeah, okay.
Because we're asking what is the angular acceleration of my pulley? And since this one is getting pulled with a tension, its force of 20 newtons, and this one, we said, well, that tension in the rope has to be less than 20 newtons because we know this is going to fall down. It's going to, obviously. But if it's falling down, that means the force up, the force from the rope, must be less than 20 newtons. So this one has a tension of 20 newtons. This has some tension or force that's less than 20 newtons. If I am applying a smaller force, the inertia, or the moment of inertia, the rotational inertia of the pulley hasn't changed. So like you were talking about, Cindy, well, that means that if the forces are the same, they would be the same, but since our forces are actually different, we're going to have different accelerations. And so this is a pretty good example of how you have to bring a force concept into a rotation problem. And that's probably what I expect them to do, but again, who knows what the test this year is going to look like. All right, do we have questions on that? Do we want me to go over it one whole time in full?
Wait, what did I miss?
Not a whole lot, I think. Just me saying, do this problem.
Ms. Jacoy, can you go over it again, please?
So, in summary, right, we have the same pulley, the same situation. The only difference is this one has more mass because there's literally a mass attached to it. And so, if we were to draw this as two different free body diagrams, are you okay with me erasing the whole question so I have room to write?
Yeah, that's fine.
Okay. So we have two situations. And so if I were to draw a free body diagram for this one for my 20 Newton object would be the force of gravity down is 20 newtons because that's its weight. And I know my acceleration is down, so that means, yes, there is a string holding it up, but that force of tension must be less than 20 newtons so that it gets pulled up or so that it falls down. It can't be accelerating up because we know that's not what's going to happen here. Whereas, so that means for my pulley doesn't see the force from the mass, it only sees the tension. And so that tension is going to be less than 20 newtons. For this one, it feels a tension of exactly 20 newtons because that's how hard we're pulling it. So this one, because we're going to have a higher force with the same radius and the same angle, and I'm going to have, this is a constant, this is a constant. The inertia of the object is constant, so that means this one is going to have a higher angular acceleration. So the angular acceleration of the second scenario will be higher than the angular acceleration of the first scenario.
Ms. McCoy,
Yes.
could you think of it as a system, like?
Yeah, and so I was actually about to go to that. So if we instead thought of it as a system, if we instead thought of it as a system, as this is the whole pulley, so this is the force on the pulley, and the 20 newtons, same thing. This is the force on the pulley. You could think of this a couple different ways. But the way I would think about it is, here's a force just on the pulley. This is a force on two objects, which means you could also think of this as F equals ma, or the idea that your rotational inertia is different because there's literally more mass there. And so in this case, you would say your forces are the same. Your r sine thetas are still constant. But your inertias wouldn't be the same because you literally have one object versus two objects. They're not going to have the same rotational inertia. It is much harder to accelerate two objects than it is to accelerate only one object. And so my inertia would go up, and inertia and acceleration are inversely proportional. So you could also think of it that way for the reason why this one is going to accelerate slower, because there's literally more objects there. There's more mass, there's more inertia, there's more resistance to acceleration. So therefore it will accelerate lower. Yeah, so this is the way I like to think of it initially. Probably if you were actually mathematically solving it, the other way would be the easier to solve it mathematically. But I think this idea makes more sense in my head at least. Because I always like to look at the whole system, not the little pieces. But both ways are important. Did that answer your question, Iceland?
Yeah, that makes sense. Thank you.
Cool. Any other questions, or we can move on to just quickly talking about what's the goal for this week. And those are the questions I wanted to go over. And if there's any questions you want to go over, feel free to look them up and ask. Okay, so this week our goal is review. I'm actually going to focus on rotation just because I think is a commonly tested, and I think for us generally our more difficult topic for us to understand. There's definitely a lot less problem sets turned in during the rotation unit than any other unit. So I'm assuming that means that it was hard for us. So for homework this week, I don't know if I've already programmed it to be dropped or I'll just do it this afternoon, but your video homework is to watch last week's officially released AP videos because they were all about rotation. And they did a very good job of this same way Mr. P does, is you do something, but we don't just say it works, they prove it works using lab technology and demos. So this week is going to be a focus on rotation, but we are going to, cover pretty much anything and everything. And then for that reason, last week, your problem set, again, I would like to get more of this in. So the problem set last week was just fundamentals. This week is going to be just random FRQ questions that I found. I'm like, this is a good question. And so again, feel free to consult people or talk to them. I highly recommend maybe setting up a, virtual study group at an appointed time every day, every week, even if it's just, you're going to talk with your friend also, but you're also like, but mom, I have to do this. This is homework. Don't you want me to do well? So that's for this week. I am going to be not assigning as much work because I know a lot of you guys are kind of some of you are give me more work. Some of you are very stressed. So I'll probably put a lot of optional assignments up. There are going to be some more mandatory assignments, but I'll throw more optional review things up so that you have them if you want them. They're there to help you, not stress you out. So if you're bored and done playing Animal Crossing, you're welcome to go and do those. All right. Any questions about the goals for this week? Next week is officially spring break. And so Eduardo, I was hoping over when we come back from spring break, we could do both Kahoots. You think you'll be able to do that? Still there, Eduardo?
He's on mute.
But he can unmute himself. I didn't do that.
Wait, Mr. McCoy.
Yeah.
So I had a question. How would I balance all the review and assignments that teachers themselves are giving, and then prep that students might be trying to do at home? So how would I balance that?
So you mean what should you prioritize, or?
Yeah, because for some of the.
So what is little g actually equal to? What's the equation for little g?
Big G,
like
M1,
big G,
M2
M1,
over R squared.
or
no.
just over
The
R
universal
over
one is
R
just over
squared.
R.
Yeah.
Right?
So
No?
the gravitational field is just 1 m. The gravitational force is 2 m's, because if you have a planet, there's a gravitational field. There is not a force until you put something on the planet. Right? If there's nothing there, nothing's going to fall because of gravity. If I put something there, then it can feel a force and be affected. So for there to be a force, there has to be 2 objects. For there to be a field, there only has to be 1 object. And so this equation is just this equation. Because when we talk about height, we really are just saying, well, this is the distance from the Earth, right? Right?
Yeah.
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 So
Yeah.
that's the difference from the Earth. AKA, it's really just a radius from the Earth. So this equation is just that. Where we're like, oh, there's a G, there's an M, there's an M, R squared times O. That cancels. And then there's a calculus reason on why it's negative due to limits and blah, 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 but we're not going to worry about that. It's a negative. And so basically, the short answer for how to solve this one is just do this equation. How many relationships are there?
3.
3. So we need to do this equation
3 times?
3 times.
What?
and add it together. Which is why I don't go over that one as much, because it tends to not end up being that hard. It's just you got to know it. So basically, all we do here is we have our G, and then This is a 2m times an m over an r squared. And so that's that relationship plus another g times a 2m times an m over an r squared. That's that relationship covered. Plus the last one, which is just a normal m times an m over r squared. And so ultimately, we just get 2gm squared over r squared. This is 2gm squared over r squared. And this is 1 gm squared over r squared. And no one corrected me that it's a single r. And then you add them up, which adds up to
5gm squared over r.
Yep, which I believe was answer D. But yeah. Oh, and then yeah, it was negative just because these are all taken to be negative.
Did you grade them all?
The FRQs, no, I have
What
not.
about the multiple choice? Have they been returned or?
They should have been returned. You should be able to see your score. Let me know if you haven't, and I'll figure out why. But no, all the multiple choice should be graded and returned. The FRQs, no. FRQs I am working on. All right, so that was number 23. Was a gravitational problem. Number 25. And so I would say like 90% of us got this question wrong, which is fine. I never taught it before. This one I'm a little more curious on why we had such a hard time with. Maybe you guys can provide me some insight. So number 25. Number 25 was a spring and potential energy problem. So we have a block on a spring, and then later, that block has descended a bit. So this is the unstretched position, and then my spring stretched and it went down 0.2 meters. So the question was, from this, what's the change in the potential energy of the system? And it was very specific. It was the spring block earth system. So the whole thing, the whole system. All right. So what do we have to do to solve this?
Use the potential spring equation.
All right, so we want to use a potential spring equation. So,
Or maybe the other one. I forgot which the other one was.
which other one?
Like
Gravitational.
All right. So how much spring potential energy does it have here in the unstretched position?
0.
0.
0.
Okay.
Oh, 0.
And then how much spring potential energy does it have in the gravitation?
0.
0.
Okay, cool. So I was actually kind of curious. We can call this our 0 point. That's fine. All right. So later, that means if this is 0, did I gain or lose potential energy?
You gained.
Yeah.
You
So I
lost
gained.
it because you're
You
going
lost it because it's
downward.
going
lost it.
in negative direction.
Okay. So yeah, so that was, excuse me, that was a vague question. I didn't specify it. So gravitationally, we definitely lost energy because we went down. But for spring potential, we stretched it, so we actually probably
Gained it.
gained it. And so we got to figure out, like, well, who won? So we basically now plug into the formula. I believe, did it give me a spring constant? Yeah. The spring constant of this is 50 newtons per meter. Anything else I need? And it's a 1 kilogram block. So they did give us all the data we need to actually solve this. So we can plug in, so this is going to be 1/2 50 times 0.2 squared. And that's going to be a positive change, and it really doesn't matter either way because that square would take care of any negatives. And then for our UG, that's going to be a negative change, 1 kilogram mass. Gravity on Earth we can take to just be 10. It's going to be a negative 0.2. And so if you do the math here, this is going to end up being, what, negative 1? No, negative 2, excuse me. So it's going to be negative 2 joules if you multiply that out. This is going to be 0.04, 0.02. I'm doing mental math, so feel free to check me before I check myself before I wreck myself.
25 times 0.04.
So
0.04. Yeah, 0.04.
so 1 joule.
Yeah.
It will be 25 times. Oh, okay, never mind. I see what you
Yeah,
mean.
so I have my decimal first. Because it's, for me, it's easier to deal with 50 than it is with 25. Same thing, it's easier to deal with a 2 than it is with a 4. So I did 0.04, 1/2 of 0.04 is 0.02, and then times 50. So 2 times 50 gives us 100, but then we have 2 decimal places, so it pops it back to a 1. Okay, so, and then I add these together, and I get
-1.
-1.
-1.
-1 joule, which is our answer. So a lot of people answered +1, and I'm not sure if that's just because we forgot about this, or we got a 1 and we're like, energy can't be negative. So I'm not sure if there's like anything that you guys are particularly confused about, or you're like, oh, I didn't understand this part of it. Would be helpful, but hopefully that makes a bit more sense now.
Wait, so energy can be negative?
So energy. So here's the thing. Energy can't be negative. Like I can't have negative 20 joules. Just like you can't own negative $20. You can lose $20 though.
Oh, so that's what it's just saying, that it lost.
Yeah, so it's not that you have a negative, because you can't have a negative. It is a scalar, but you can have a negative change in it.
So this is just the change in energy.
So the negative just says that it's losing it.
Yep.
Amount.
Net loss.
Okay.
So yeah, so that's, and so I know because I say like it's a scalar, it can't be positive or negative, and this is true, but that doesn't mean you can't have a negative change. So you can't own negative $20, but you can lose $20 to somebody. That's very possible. Basically, energy doesn't have a left or a right. It doesn't have a direction, but you can gain or lose it. So in that sense, the negative implies the change, not the actual state of existence. Good question. All right, we cool to go to another one? Do we need to take a break? Shake it out? I'm only going to go over a couple more because I don't want to overwhelm you guys. Are there any that you in particular really, really, really want to go over? Or I'll just do the 2 that I wanted to go over and it'll just be my choice.
Yeah.
All right. This is also one that we had trouble with, which is something that I keep telling you guys, they're going to find ways to trick you with this, and every time, it's still the same answer. And this is, of course, a center of mass problem. So, what do we know about an object's center of mass? Or its state of being? What is the object's center of mass?
The middle.
Right in the middle.
Right in the middle. So this problem was it set it up like an experiment. So it was in trial 1 of experiment, a cart moves with some initial velocity and hits another cart. That was, I think, still, and collides elastically, so they bounce.
Mhm.
Trial number 2, it hits with some initial velocity, but they stick and they move together. The question is, how does the speed of the center of the two-cart system center of mass change, if at all, during the collision in each trial?
It's conservation of momentum.
This is a conservation of momentum problem. Basically, they're asking who has more momentum at the end. Who has more momentum at the end?
Is object
The
2
one that-
still?
Huh?
Is object 2 like not moving?
No, they just stick together. They're still moving, but it's just like a class where like one was just two cards and they bounce, and the other was two cards and they stick.
So that's but they so the top I mean for one it was just still, right? Like and then the first card bumped into it and then they started moving.
Yeah. So for both of them, this car started from rest, and then this one they bounced off each other elastically. This one was completely inelastic. They stuck together.
Oh, collisions.
And then what did the question ask?
The question was, how does the speed of the cart's center of mass change, if at all?
It shouldn't because it's conservation of
And
momentum.
so the correct answer
It
does not change. All right, and then we'll go for the second one because it's spread it out.
doesn't need it.
Does trial 2 change?
No.
No, it does not change.
Okay. Mm.
Pretty much anytime they ask you a center of mass problem, it's just a conservation momentum problem. And they're like, was momentum conserved? And unless there's some outside force, the answer is yes. Yes, it is. It does not change.
Wait, Mr. Coy, so unless there's an outside force, every like collision momentum is conserved.
Yes.
Okay.
And so it's hard for us to see because there's almost always the outside force of friction when we view collisions because friction's everywhere. And we never got the computers to actually do the really good. I might try to make a demo of it. It's really hard to do though, alone especially. I was actually going to have us at the end of the year do a lab proving that momentum is conserved in 2 dimensions. Because I have these little hover soccer balls, so you can hit them at each other. And then if you add up your X and your Y, you actually get that it's the exact same this started with in the X and the Y.
Is it like air hockey?
Yeah, it is, except like it's a little hovered soccer ball.
Oh,
thing.
yeah. I remember.
So I was really looking forward to this lab, but it's not happening, so that's okay.
Mr. Core.
Yeah.
So if they weren't considered like a system, then it wouldn't be conserved.
So yeah. So for example, if they were asking instead, how does the center, the speed of the center of mass of object number 1? If they instead focused on that one object, then yeah, it would change, right? Because this is obviously not going the same speed it was going before it hit the second cart. And so they almost always do it as a whole system, but you're right. If they ask about an individual piece, then this would be your outside force. And in that case, it would change because there was an outside force acting on it. So we're going to see F equals ma. There's going to be some sort of acceleration because there was some sort of net force. Great question. All right, any other questions on center of mass? Because I don't know if it's going to come up in the FRQ. If there was multiple choice this year, I'd say there's 100% going to be some center of mass question where they try to make it sound like something changes and it's actually just the same. Free response, I don't know, maybe. Questions about this?
No.
All right, then I'm going to do 36, and then if you guys have any questions, otherwise we'll call it a day. Feel free to next time look up questions in between now and Wednesday and come up with any questions that you would like to ask. It's actually a great idea, because I don't want to do like where you sit down and go over all of it, because that's a lot to go over. But I'll absolutely take individuals. Okay, this is a graph question. I regret trying to draw this, but basically, this is a kinetic energy problem, 36. And so we're given a force spring length graph. Okay. Before I even put numbers on here, what type of graph is this?
Work.
It's a work problem. How do we know it's a work problem?
Because force times displacement equals work.
They give us some force and displacement. So I'm going to put some numbers up here. 2, 3, 5, 6. So these are tens, but 0.2 goes at 60. 0.3 is all the way at 0. So they don't draw the line, but pretty much that's a triangle if I ever saw one. And so what do we do to find work on these?
You look at the area.
Yeah.
So what's the base of this triangle?
0.1.
0.1. What's the height of my triangle?
60.
60, yeah. And then it's a triangle, so it's
1/2.
1/2. So that would be 30 times 0.1, which just means I move my decimal. So that gives us 3 joules. And so when I do this, always look at the graph, because anytime they give you this, they're either directly asking about the force or acceleration, i.e. F equals ma, or it's probably a work problem. And they don't make it sound like that because they ask, what is the kinetic energy when the block leaves the spring? What is one of the definitions for work?
The change in kinetic energy.
The change in kinetic energy. And they said it was released from rest. So if the change in kinetic energy is my work, and my initial kinetic energy is 0, that means my kinetic energy is my work. So the correct answer is
3 joules.
3 joules.
Wow.
And so that's why before you even read the problem, really look at your graph. Because like Catalina didn't even know what the problem was, but she was like, we can find work from this. Absolutely. And so most of the graph problems, and this applies for the FRQ too, like before you even read what are they asking, like, okay, what type of graph is this? What things can this tell us? Obviously it can tell us force and spring length. If we do the area, we can find the work. If we do the slope, I don't really know what that means, so probably we're not going to use the slope, because that would be force divided by distance, which is kind of an odd thing. Like, I don't know what that is. So we probably don't need to worry about what it is. And so that gives you pretty much 2 options on you either read this graph to help you or you find the area of this graph. They're going to make you do one of those 3 things, though, slope, area, or read it. All right. Are there any questions you guys would like to go over or something you'd want me to talk about a bit more? Otherwise, we will call it a day here. Keep class to under an hour.
What topics do you think will be on the AP test?
They're going to probably do, I gotta go look back at the wording if they're gonna do 2 or 3 problems. Definitely it's gonna be more like your English is probably gonna be like 1 essay.
I thought it was gonna be 1 to 2 for all the.
Yeah, and so that's what I think. So that means it's gonna be 2 problems, and that tells me if it's 2 problems in 45 minutes, they're gonna give you 1 long one and 1 short one. I'm gonna guess one's gonna be a paragraph. And then the other one is either a lab or a qual quant. The labs being you write up a lab, like we talked about. So we'll definitely practice more of those. The qual quant is where they make you look at a situation and explain it and probably derive an equation and also be like, but if we change this, conceptually what's going to happen? I'm not sure which one they're going to value more over a lab or a qual quant because those are both considered like cornerstones, like they're always on the test. So, I mean, the topic. So let's throw up, what are the fair game topics? We have kinematics.
Forces.
Rotational.
Rotation.
Momentum. Energy.
Definitely 100% there's going to be energy. I can't imagine. Energy is such a huge part of this test. One of the FRQ questions is absolutely going to have to do with energy.
Simple harmonics.
And simple harmonics. And so I would personally expect this to be most of it. We're probably going to get tiny tie-ins to these. Could I be wrong? Absolutely. But
they would like not emphasize rotation.
No, there's definitely there's of the 5 years they've done this test, 4 of those years rotation has been an FRQ question. So it's highly expected, but I expect them to tie in, if they are doing a rotation question, I expect them to either tie in forces, momentum, or energy into that question. Like, I don't think it's going to be a purely rotation question, which makes sense because rotation is just all of these things but spinning.
So it would be more of like a complex question rather than just like a single topic.
Which, if you guys kind of remember looking at a lot of your FRQs, almost all of them are like dual. So I expect them to really be playing on that. I expect them to hit most of these. I would, if they're going to knock out anything, I'm not going to really cover simple harmonic motion as much. It's normally considered maybe 10% of the test, and when they make the test this short, if there is a question, it's probably not going to be worth a ton of points because forces, energy, momentum are a large part of, like, proportionally what that should be. Since I know we have trouble with rotation, I really want to focus on rotation. I know we have trouble with forces.
Yes.
And then I'm going to really cover those next, just because they're big topics. We normally do pretty well with momentum and kinematics, but we are going to review them for good measure. But again, the best review is almost always like, let's just do as many FRQ questions as I can find. And so probably each review session, I'll have at least one FRQ question ready and put it up on the board for you guys. Probably even send it out via Google Classroom so we can look at it together and you can take a crack at it before we do it as a class.